planet exists that should be impossible. Its density doesn't match anything our models predict. Another world drifts utterly alone through the galaxy, bound to no star, formed by no system we fully understand. A third orbits its sun backwards, moving against the very spin that birthed it. These are not theories. They are confirmed, measured, photographed. For decades, scientists built an elegant rulebook for how planets must form, where they must orbit, what they must weigh. That rulebook is now being quietly rewritten, one impossible world at a time. Tonight, we walk through the planets that broke the rules, and what their existence is teaching us about everything we thought we understood. There's something quietly comforting about learning alongside people who are just as curious as you are. And if that's you tonight, liking and subscribing helps more of these journeys find their way to you. No pressure at all, just a genuine thank you for being here. Get cozy and let your eyes rest a while. In 3, 2, 1, liftoff. Right now, somewhere in the darkness between the stars, a planet is moving in a direction it should not be moving in, around a star it should not be orbiting in that way, at a density that should not be possible for a world of its size. Astronomers built careful rules for how planets are supposed to form, rules based on decades of observation and physics that has worked everywhere else we have tested it. And then real worlds, confirmed, measured, photographed worlds, started breaking those rules in ways nobody predicted. This is the story of 3 of those worlds, and what their existence is forcing scientists to admit about the limits of their own best theory. To understand why a planet can break the rules, you first have to understand what the rules actually are. Planet formation theory did not appear out of nowhere. It emerged from watching young stars across the galaxy, measuring the disks of gas and dust that surround them in their infancy, and comparing those disks to the planets we eventually find orbiting older, more settled stars. The basic recipe sounds almost too simple for something that built every world we know of, including the one under your feet. A star forms first, condensing out of a collapsing cloud of hydrogen and helium left over from the earliest chemistry of the universe. As that star ignites, a flattened disk of leftover material spins around it, gas and dust caught in orbit, slowly cooling and settling into a thin plane, the same plane that would one day become the orbits of every planet in that system. Inside that disk, tiny grains of dust begin to stick together. At first, this happens through simple static forces, the same kind of effect that makes dust cling to a balloon. Over time, these grains build into pebbles, then boulders, then bodies, large enough that gravity itself takes over the job of attracting more material. This process is called accretion, and astronomers have watched versions of it happening right now in young star systems scattered across our galactic neighborhood, using infrared telescopes capable of piercing through the dust that would otherwise hide the process entirely. As these growing bodies sweep up more and more material, they eventually become what scientists call planetary embryos, objects large enough to dominate their local region of the disk gravitationally. Closer to the star, where temperatures are too high for ice to survive, these embryos are built almost entirely from rock and metal, the heavier elements that condense first as the disk cools outward from its blazing center. Farther from the star, beyond what astronomers call the frost line, ice becomes stable, and the embryos that form there can grow much larger, eventually massive enough to gravitationally capture huge envelopes of hydrogen and helium gas directly from the surrounding disk before that disk disperses. This is, broadly, why our own solar system looks the way it does. 4 small rocky worlds close to the Sun, and 4 enormous gas and ice giants farther out, with an asteroid belt marking roughly where the frost line once sat. This same basic division of rocky inner worlds and gas-rich outer worlds was, for decades, treated as something close to a universal law, the expected outcome of any star system given enough time. From this formation process, astronomers can do something remarkable. They can calculate, with real mathematical precision, what a planet's density should be based on nothing more than its mass and its radius. Density is simply mass divided by volume. How much material is packed into a given amount of space? A planet built almost entirely from rock and iron, the way Earth is built, should have a density somewhere in the range of 5 to 6 grams per cubic centimeter. Water ice, by contrast, has a density of roughly 1 gram per cubic centimeter, and a thick envelope of hydrogen and helium gas is dramatically less dense still, sometimes less than 1 gram per cubic centimeter for the puffiest gas giants. So when astronomers measure a planet's mass, usually through the gravitational wobble it induces in its host star, and its radius, usually through how much starlight it blocks as it passes in front of that star, they can combine those two numbers and ask a very direct question. Does this planet's density match what we would expect from a world built the way our formation models predict? Most of the time, the answer is close enough. The vast majority of the more than 5,600 confirmed exoplanets discovered so far fall into reasonably predictable density ranges for their size and the temperature of their environment. But a growing number do not, and the gap between prediction and reality is not a rounding error. It is sometimes a difference so large that it forces a complete rethinking of what the planet must be made of, or how it must have formed, or both. These are not theoretical objects dreamed up to test a hypothesis. They are real planets, sitting in real telescope data, refusing to behave the way the textbook says they should. The first world that breaks this rulebook orbits a star so close that its entire year, the time it takes to complete one full orbit, lasts less than 11 hours. This is a planet called TOI 561b, and it belongs to a category astronomers call ultra-short period planets, worlds that complete an orbit in under 24 hours, sometimes far less. To put that in perspective, Mercury, the innermost planet of our own solar system, takes 88 days to orbit the Sun. TOI 561b completes more than 2 full orbits in a single Earth day. It sits less than 1 million miles from its star, a distance so small that compared to the separation between Mercury and our own Sun, it is roughly 1/40th as far. At that distance, the star's gravity has long since locked the planet into what astronomers call tidal locking, meaning the same side of the planet always faces the star, exactly the way the same side of the Moon always faces Earth. This permanent dayside sits under radiation so intense that surface temperatures comfortably exceed the melting point of ordinary rock. We are not talking about a hot desert or a scorched plain. We are talking about a planet whose sunward face is, in all likelihood, a standing ocean of molten stone, a magma ocean kept liquid by a star that never sets and never dims. Given that environment, the leading models of planet formation made a fairly confident prediction about what TOI 561b should be. A rocky world this close to its star should have lost any primordial atmosphere almost immediately. The intense radiation from the star should strip away light gases like hydrogen and helium within the first few million years of the planet's existence, a process astronomers call photoevaporation. What should remain, the models said, is a bare rock, dense, airless, essentially a slightly larger, much hotter cousin of Mercury. When astronomers calculated TOI 561b's density using its measured mass and radius, the number that came back did not match that prediction. The planet's measured density came out anomalously low, lower than an Earth-like composition of rock and iron would produce. This was not a small discrepancy that could be explained away by measurement uncertainty. It was low enough that the research team behind the discovery, led by Carnegie Science staff scientist Johanna Teskey, described it explicitly as distinct from what an Earth-like composition would predict. A planet this size, orbiting this close to its star, should be dense. Instead, it was behaving more like a world with either an unusually light rocky mantle or, more provocatively, a world that still somehow retained some kind of atmosphere, despite conditions that should have stripped any such envelope away within the planet's earliest geological history. For years, this anomaly sat as an open question, one of those nagging discrepancies that gets noted in a paper and then waits for better instruments to resolve it. The resolution came through observations using the James Webb Space Telescope's infrared instruments, specifically the near-infrared camera and the mid-infrared instrument, tools sensitive enough to detect the faint thermal signature of gases glowing in a planet's dayside atmosphere, even when that planet orbits a star hundreds of light years away. What those observations revealed, published in research led by Teskey's team, was that TOI 561b is surrounded by a thick blanket of gas sitting directly above its molten dayside surface. This was not the kind of thin, residual wisp of atmosphere you might expect to find clinging to a planet that mostly lost its envelope billions of years ago. The brightness temperature measurements, essentially how hot the dayside appears to glow in infrared light, required a genuinely substantial atmosphere, one thick enough to actively redistribute heat away from the side facing the star, something a bare, airless rock simply cannot do. This single result rewired the explanation for the planet's strange density. A rocky world, without any gas envelope at all, should be dense and compact, all of its mass concentrated into solid rock and metal, with nothing puffing up its measured radius. But a rocky world that has somehow retained, or perhaps continuously regenerated, a thick volatile envelope, likely dominated by carbon monoxide or carbon dioxide, outgassed directly from an active magma ocean below, would measure a larger radius for the same underlying mass, which is exactly what produces a lower calculated density. In other words, TOI 561b is not lighter because it lacks rock and iron at its core. It is lighter because something is actively pumping volatile gas into its surrounding envelope from below, likely sourced from the magma ocean itself, releasing gas as it churns under extreme heat and pressure, faster than starlight can strip that gas away. There is an additional detail about this star system that makes the puzzle even stranger. TOI 561 sits in a region of the Milky Way known as the thick disk, a population of stars that are, on average, far older than typical stars, like our own Sun, and noticeably poorer in heavy elements, the metals that astronomers use as shorthand for anything heavier than hydrogen and helium. The host star is roughly twice the age of our own Sun, and significantly more metal-poor. Planet formation models generally predict that metal-poor stars, having formed from clouds of gas with less heavy element content to begin with, should produce planets with thinner, less substantial rocky cores, simply because there was less raw material available to build them from. TOI 561b, sitting around exactly this kind of ancient, metal-poor star, fits that broader prediction reasonably well in terms of its overall mass. But the specific combination, an ancient, metal-poor star hosting a planet that nonetheless manages to sustain an actively replenished volatile atmosphere under blistering ultra-short period conditions, was not something the standard models anticipated. The planet is rewriting the assumption that ultra-short period worlds are uniformly destined to become bare, dead rocks. This is not an isolated curiosity. TOI 561b belongs to a small but growing cluster of similarly observed worlds that are forcing a broader reassessment of what ultra-short period planets are actually like. Researchers studying another nearby ultra-short period world, 55 Cancri E, used the same James Webb instruments to detect a persistent volatile envelope inconsistent with a bare rock interpretation, again likely dominated by carbon monoxide or carbon dioxide. Another world, TOI 561b's distant cousin TOI 561b itself aside, a separate, ultra-short period planet called TOI 561b, sits alongside research into TOI 561b. The pattern holds across multiple, independently studied systems. Lava worlds, it turns out, are not simply dead, stripped husks. Some of them appear to be geologically and atmospherically active in ways that directly contradict the simplest version of the photoevaporation model. Now consider the opposite extreme, a planet at the other end of the density spectrum entirely. While TOI 561b is anomalously light for its size, a separate world called GJ367b sits almost exactly on what astronomers call the iron sequence, the theoretical line on a mass radius diagram that represents a planet made almost entirely of pure iron, with essentially no rocky mantle surrounding that core at all. To put this in context, Earth is roughly 32% iron by mass, with the rest made up of silicate rock forming the mantle and crust around that iron core. A planet sitting on the iron sequence would need a mass fraction of iron dramatically higher than that, potentially approaching 90% or more of its total mass concentrated into a metallic core, with only the thinnest residual layer of rock on top, if any rock remains at all. Imagine holding two objects of identical size in your hands, one a rocky stone the size of a marble, the other a solid sphere of iron of that exact same size. The iron sphere would feel dramatically heavier, because iron packs roughly 3 times more mass into the same volume that ordinary rock does. GJ367b is, in effect, behaving like that iron sphere rather than that stone, despite occupying a size category that planet formation models generally expect to be dominated by rock, not metal. The leading explanation scientists are currently testing for this kind of extreme, iron-dominated world is sometimes called the stripped core hypothesis, though it remains genuinely debated rather than settled. The idea proposes that a planet like GJ367b did not form this way originally. Instead, it may have begun its existence as a larger, more ordinary rocky planet, complete with a substantial silicate mantle surrounding an iron core, the same basic layered structure Earth has. At some point in that planet's early history, the hypothesis suggests a massive collision, a true giant impact on the scale of the event thought to have formed our own moon, could have violently stripped away most of the planet's outer rocky mantle, blasting it into space and leaving behind a battered remnant dominated by the dense iron core that survived the impact intact. This is sometimes called the giant impact stripping pathway. A competing explanation suggests that rather than a single violent collision, intense radiation from a young, active host star may have slowly evaporated away lighter material from the planet's outer layers over a longer period, gradually concentrating the surviving mass into a denser, more metal-rich remnant. Neither explanation has been confirmed beyond reasonable doubt, and research published examining the broader population of so-called supermercuries, the informal name for this class of extremely dense, iron-rich worlds, has found no compelling evidence that this category is even definitively real as a distinct population, separate from ordinary statistical scatter in mass and radius measurements. Though GJ367b itself remains widely treated as a strong individual candidate, sitting unusually close to the iron sequence line in a way that is difficult to explain through measurement uncertainty alone. Researchers running planet formation simulations have found that supermercury worlds appear more likely to form around stars with a low ratio of magnesium to silicon in their composition, a subtle chemical fingerprint that affects what kind of minerals condense first as a planetary disk cools. This is a genuinely active area of research, with new candidate worlds, including a recently characterized system called TOI 4552b, joining the small list of ultra-short period worlds considered favorable for further atmospheric and compositional study using the next generation of space telescopes. What makes both of these worlds, TOI 561b and GJ367b, so significant is not simply that they are unusual. It is that they sit at opposite ends of the exact same physical category, ultra-short period planets orbiting dangerously close to their stars and yet produce dramatically different outcomes. One retained, or somehow regenerated, a thick volatile envelope that current photoevaporation models did not predict it could keep. The other appears to have lost so much of its rocky material that it now resembles almost pure metal, more extreme than the stripping process was expected to typically produce. The standard model predicted a narrow, fairly uniform outcome for planets in this orbital category, stripped, bare, rocky worlds clustered around a fairly predictable density. The real population of ultra-short period planets observed so far spans a much wider range than that prediction allowed for, and each individual world that breaks the expected pattern forces researchers to add new physics, new formation pathways, new exceptions to a model that was originally built to be elegantly simple. This is the first crack in the rulebook, and it is an important one to sit with before moving forward, because it establishes something that will matter for everything that follows. Planet formation theory is not wrong in any broad sense. It correctly predicts the overall architecture of most planetary systems, the general division between rocky inner worlds and gas-rich outer worlds, the basic physics of how a disk of gas and dust around a young star collapses into discrete bodies over millions of years. But the theory's confidence in predicting the specific, fine-grained details of any individual planet, exactly how dense it should be, exactly what its interior should be made of, is being tested and, in some cases, quietly revised every time a new ultra-short period world gets its density measured with sufficient precision. The rulebook still works as a general guide. It has simply stopped being treated as a set of rigid, universal laws that every planet must obey without exception. And density is only the first category of rule that real planets have been found breaking. The next anomaly does not concern what a planet is made of at all. It concerns something far stranger: whether a planet needs a star in the first place. Every model of planet formation described so far begins with the same fundamental assumption. A star forms first, and a disk of leftover material spins around that star, eventually clumping together into planets bound by that star's gravity for the rest of their existence. This assumption is so deeply built into the language astronomers use that the very definition of the word planet, as adopted by the International Astronomical Union, includes orbiting a star as one of its core requirements. A planet, by the strict technical definition, cannot exist without a star to orbit. And yet, scattered across the galaxy, astronomers have now confirmed the existence of objects with planetary masses that orbit no star whatsoever, drifting alone through the vast emptiness between star systems, untethered to any gravitational anchor at all. These objects are called free-floating planets, sometimes referred to more casually as rogue planets, and for a long time they existed mostly as a theoretical curiosity, a logical possibility that fell out of the mathematics of planet formation without much direct observational evidence to confirm they were common, or even that they existed in meaningful numbers at all. The basic theoretical case for their existence was simple enough to imagine. Young planetary systems are violent, chaotic places in their earliest millions of years. Multiple planets, sometimes far more than the handful that survive into a system's stable old age, jostle for position in close, overlapping orbits, exchanging gravitational tugs that can fling lighter or less fortunately positioned worlds completely out of the system entirely, hurling them into interstellar space at speeds great enough to escape their star's gravity forever. A planet ejected this way does not stop existing. It simply stops belonging to anyone. For decades, finding such an object seemed like an almost impossible task. The two primary methods astronomers use to detect planets: the transit method, watching for the tiny dip in starlight as a planet crosses in front of its star, and the radial velocity method, measuring the gravitational wobble a planet induces in its host star. Both depend entirely on the planet having a host star to begin with. A planet with no star produces no transit because there is no background starlight for it to dim. It produces no measurable wobble because there is no star to wobble. By every conventional detection method available, a free-floating planet should be invisible, a needle hiding not just in a haystack, but in a haystack with no needle ever expected to be found. The method that finally cracked this problem is called gravitational microlensing, and it relies on one of the stranger consequences of Einstein's general theory of relativity. According to that theory, any object with mass bends the fabric of space and time around it, and light traveling through that bent space follows a curved path rather than a straight one. Most of the time, this effect is too subtle to notice, but occasionally, by pure chance, a massive object happens to pass almost exactly between Earth and a much more distant background star. When that alignment happens, the gravity of the closer object acts like a lens, bending and focusing the light from the distant star behind it, causing that background star to appear briefly, dramatically brighter than normal, sometimes for just a few hours, sometimes for several days, before fading back to its ordinary brightness as the alignment passes. Crucially, this lensing effect does not require the foreground object to emit any light of its own. A planet with no star, drifting through the darkness completely invisible to direct observation, can still be detected this way, not by seeing the planet itself, but by watching the characteristic brightening and fading of a distant background star as the planet's gravity briefly passes in front of it from our perspective. The technique is extraordinarily difficult in practice. These alignments are rare, unpredictable, and happen only once, since the foreground object and background star are both moving through space and will never again line up in exactly that configuration. Astronomers running dedicated microlensing surveys must monitor enormous numbers of background stars continuously, every single night, waiting for the brief, unrepeatable signature of an unseen object passing in front of one of them. For years, microlensing surveys did detect a population of these short, planet-scale brightening events, and the population statistics strongly suggested that many of the responsible objects were less massive than Jupiter, consistent with free-floating planets rather than larger stellar mass objects. But there was a frustrating limitation built into the method itself. A single microlensing event, on its own, cannot distinguish between two very different possible scenarios. A small, nearby object could produce exactly the same brightening signature as a larger, more distant object, because the strength and duration of the lensing effect depends on a combination of both mass and distance, woven together in a way that a single observation simply cannot separate. Astronomers call this entanglement the mass-distance degeneracy, and for years it meant that even when a free-floating planet candidate was detected, scientists could only estimate a range of possible masses and distances, never a single confirmed value for either one individually. This changed with a discovery announced in a paper published in the journal Science at the very beginning of 2026. A team led by astronomer Subo Dong observed a microlensing event using both ground-based telescopes and a space-based observatory simultaneously, watching the same brightening signature from two dramatically different vantage points at once. This dual perspective is the key that finally broke the degeneracy. Because the two observing locations, one on Earth's surface and one in space, see the lensing event from slightly different angles, comparing the two observations directly reveals information that a single telescope, watching from a single vantage point, simply cannot extract on its own. This technique is called space-based microlens parallax, and applying it to this particular event allowed the research team to do something that had never been done before for a free-floating planet candidate: measure both its mass and its distance independently and precisely, rather than as a tangled, ambiguous combination of the two. The result was an object with a mass close to that of Saturn, either gravitationally unbound entirely, drifting completely free through interstellar space, or just possibly orbiting on an extremely wide, distant path around some star, too faint and too far away for current instruments to detect directly. This distinction matters enormously for what the discovery tells us about formation. The research team's analysis pointed toward a specific origin story for this particular object. Its measured mass suggested it most likely did not form the way a star or a brown dwarf does, through the direct gravitational collapse of a cloud of gas condensing under its own weight. Instead, the evidence favored a planetary origin. The object most likely began its existence inside a protoplanetary disk, built up gradually through the same accretion process that built every rocky and gas giant planet in our own solar system, before being violently cast out of its system entirely by some dynamical event in its youth. In the words of the research team itself, published directly in their paper, the conclusion drawn from this measurement was that violent dynamical processes shape the demographics of planetary mass objects, both those that remain bound to their host stars and those that are expelled to become free-floating. This is a remarkable sentence to sit with, because it reframes free-floating planets not as some separate, exotic category of object entirely distinct from the planets in our own solar system, but as the casualties of the exact same chaotic, competitive process of planet formation that built every world we know, including our own. Our solar system's 8 surviving planets are not the entire story of what our own protoplanetary disk once produced. They are simply the survivors, the ones that found stable, lasting orbits, while other, less fortunate bodies, quite possibly entire additional planets formed in our own system's earliest history, were flung out into the darkness, millions or billions of years ago, never to be seen again. This particular free-floating planet sits at a distance of roughly 9,950 light-years from Earth, toward the dense, crowded region near the center of the Milky Way, an area where the sheer density of stars makes microlensing alignments far more likely to occur and far more likely to be caught by the dedicated survey telescopes, scanning that region continuously. But this is far from the only evidence supporting the existence of free-floating planets. Independent confirmation has also come from an entirely different observational approach, this time using direct infrared imaging rather than microlensing at all. When the James Webb Space Telescope was pointed toward a star-forming region called NGC 1333, located in the constellation Perseus, roughly 960 light-years away, astronomers using the telescope's extraordinary infrared sensitivity discovered 6 separate planetary mass objects within the nebula that appear to have formed independently of any star at all. Unlike the microlensing detections, which infer a planet's existence indirectly through its gravitational effect on background starlight, this discovery involved directly imaging the objects themselves, faint, cooling bodies, still glowing, with residual heat left over from their own formation, embedded within the same dense, collapsing clouds of gas and dust that are actively forming new stars all around them in that same nebula. This finding is significant because it points toward a second, genuinely distinct formation pathway for free-floating planets, one that does not require any prior star or ejection event at all. Rather than being violently expelled from an existing planetary system, these objects in NGC 1333 appear to represent cases where a clump of collapsing gas and dust, the same basic raw material that would normally condense into a star, instead formed a body too small and too low in mass to ever ignite nuclear fusion in its core, the defining threshold that separates a true star from everything smaller. Researcher Adam Langeveld of Johns Hopkins University, who worked on this discovery, described the team as probing the very limits of the star-forming process itself, directly asking the question of whether an object that resembles a young Jupiter could, under sufficiently different starting conditions, have instead become a star. One detail from this discovery adds an entirely new layer of strangeness to the picture. None of the 6 planetary mass objects found in NGC 1333 came in below roughly 5 times the mass of Jupiter, despite the James Webb instruments being sensitive enough to detect objects considerably smaller than that if they existed in this region. This absence of smaller objects may indicate that there is a genuine minimum size threshold for any body that forms directly through the gravitational collapse of a cloud, a flaw below which the cloud collapse process simply does not produce a stable, isolated object, rather than smaller bodies simply being too faint or too cool to detect with current instruments. If that interpretation holds up under further study, it would mean that truly small, Earth-sized or even Neptune-sized free-floating planets, the kind directly comparable in mass to the planets in our own solar system, likely cannot form through this particular cloud collapse pathway at all. Their existence, if confirmed elsewhere in the galaxy, would have to be explained almost entirely through the violent ejection pathway instead, the same dynamical process responsible for the Saturn mass object, measured through microlensing toward the galactic center. Perhaps the most genuinely surprising detail to emerge from the NGC 1333 observations was the discovery that one of these 6 free-floating objects appears to be surrounded by its own dusty disk of material. This is a profound finding because a disk of leftover gas and dust orbiting a body is exactly the kind of structure that, around a star, would eventually be expected to form planets of its own through the same basic accretion process described earlier. The presence of a disk around an object that is itself not orbiting any star at all raises a genuinely open question that current research has not resolved: whether entire miniature planetary systems, worlds orbiting other worlds, with no star involved in the configuration at all, could form and exist as stable, self-contained structures drifting through interstellar space, completely independent of any star's gravity from the very beginning of their existence. Standing back from the individual details, the overall picture that emerges from combining the microlensing measurement near the galactic center with the direct imaging results from NGC 1333 is that free-floating planets are not some vanishingly rare statistical curiosity confined to the edges of theoretical possibility. The lead researcher on the January 2026 microlensing paper stated directly that the discovery offers further evidence that the galaxy may be teeming with rogue planets. That word, teeming, is a striking choice for a population of objects that, only a few decades ago, existed purely as a hypothetical consequence of planet formation models, never confirmed, never directly measured, treated as an interesting footnote rather than a genuine category of cosmic object worth dedicated searching. Current astronomers now estimate, based on the statistics gathered from years of microlensing surveys, that free-floating planets may significantly outnumber the stars themselves across the galaxy, though the precise scale of that population remains an active area of ongoing research rather than a settled figure. What makes this anomaly category so different from the density anomalies explored earlier is the nature of the rule it breaks. TOI 561b and GJ367b violated specific quantitative predictions about composition, numbers that could be calculated and compared directly against measurement. Free-floating planets violate something more fundamental than a single calculated prediction. They violate the basic architectural assumption sitting underneath the entire framework of planet formation theory, the assumption that a planet's identity is inseparably tied to the star that birthed it. A planet, in the traditional sense, has always been defined partly by its relationship to a star, by an orbit, a year, a defined gravitational dance lasting for as long as that system endures. A free-floating planet has none of that. It has no year, in any meaningful sense, because it traces no orbit around anything at all. It has no sunrise, no sunset, no defined position in any system's architecture. It simply exists, alone, carrying within it the same fundamental building blocks of rock, metal, ice, and in some cases atmosphere, that every other planet is built from, but utterly severed from the one relationship that planet formation theory always assumed was non-negotiable. The two formation pathways, now under serious scientific consideration, violent ejection from an existing system on one hand, and independent collapse directly from a cloud of gas and dust on the other, are not mutually exclusive explanations, competing for a single correct answer. The current evidence increasingly suggests that both pathways are real, and that the free-floating planets scattered throughout our galaxy likely represent a mixed population, drawn from both origins simultaneously, indistinguishable from each other through mass alone, distinguishable only through painstaking individual case studies. New research into how rogue planets can form naturally within young, crowded star clusters has added a further layer of detail to this picture, suggesting that gravitational interactions between the dusty, planet-forming disks surrounding multiple young stars sitting close together in a dense cluster could themselves eject material directly, producing free-floating objects through close encounters between neighboring systems before those systems have even finished forming their own permanent planets. This adds a third possible mechanism into the mix, alongside violent ejection from a single mature system and independent collapse from a cloud, layering further complexity onto a category of object that, only a generation ago, was not confirmed to exist at all. The Nancy Grace Roman Space Telescope, expected to begin science operations in the coming years, has been specifically designed with this population of objects in mind. Its wide field of view and exceptional infrared sensitivity will allow it to conduct microlensing surveys, covering far larger areas of sky, far more efficiently than the current generation of ground-based instruments are capable of, scanning for the brief, unrepeatable, brightening signatures that reveal free-floating planets without ever directly imaging them at all. Researchers anticipate that this single mission alone could multiply the confirmed population of known free-floating planets by a significant factor within just the first few years of operation, finally providing the large-scale statistical sample needed to determine, with real confidence, how common these starless worlds actually are across the wider galaxy, and what fraction trace back to each of the formation pathways currently under consideration. What we are left with, after walking through both the density anomalies of Part 1 and the starless worlds of this section, is a steadily widening picture of just how much variation real planets are capable of producing, far beyond what the cleanest, simplest version of formation theory ever anticipated. A planet can retain an atmosphere it was never supposed to keep. A planet can lose so much of its rocky material that it resembles a sphere of nearly pure iron. A planet can lose its star entirely, drifting alone through the galaxy for the rest of its existence, carrying no orbit, no year, no fixed place in any system at all. Each of these worlds breaks a different assumption built into the rulebook, and yet none of them breaks the underlying physics holding the universe together. They break only the narrower, more specific predictions astronomers built on top of that physics, the predictions that assumed planet formation would behave in a tidier, more uniform way than it actually does. There remains one more category of rule-breaking world left to examine, and it concerns neither what a planet is made of, nor whether it has a star at all, but something even more fundamental to the basic architecture of any orbiting system: the direction in which a planet moves. Every planet you have ever heard of, every world drawn in every textbook diagram of a solar system, shares one quiet assumption that almost nobody bothers to state out loud, because it has always seemed too obvious to need saying. Planets orbit in the same direction their star spins. This is not a coincidence, and it is not a minor footnote. It is one of the most basic predictions to fall directly out of the very first stage of planet formation described earlier. The collapsing cloud of gas that gives birth to a star and its surrounding disk in the same continuous motion. Now, deep in a system roughly 540 light-years away, sits a planet that breaks this rule outright. A planet caught mid-transformation, orbiting its star backward. To understand why this matters so profoundly, it helps to return to the very beginning of the formation story, the same collapsing cloud described in part 1. When a cloud of gas and dust begins to contract under its own gravity, it almost never starts out perfectly still. Even the faintest, most negligible rotation present in that cloud before collapse begins gets dramatically amplified as the cloud shrinks. In exactly the same way, a spinning ice skater speeds up when she pulls her arms in close to her body. This effect, called the conservation of angular momentum, means that a slowly rotating cloud of gas, as it collapses down into a much smaller, much denser star, ends up spinning far faster than it started. And critically, it spins in one single, consistent direction throughout the entire process. The star that forms at the center inherits this spin directly. The disk of leftover material that flattens out around that star inherits the very same spin, moving in the very same direction, because both the star and the disk condensed out of the exact same rotating cloud at the exact same time. Every planet that subsequently forms within that disk, built from material orbiting in that established direction, should naturally end up orbiting the same way the star itself is spinning. This is called a prograde orbit, and under the standard model, it is not simply the most common outcome. It is supposed to be close to universal for any planet that formed through ordinary disk accretion. A planet orbiting in the opposite direction against the spin of its own star is called retrograde, and for a long time such an orbit was treated as something the standard model could not easily produce at all. If the planet formed directly from the disk, moving in lockstep with the material that built it, there should be no straightforward mechanism within ordinary disk accretion to flip that planet's direction of travel after the fact. Early theoretical work on giant planet migration, the gradual inward drift that explains how massive worlds end up orbiting far closer to their stars than the location where they originally formed, generally assumed that gravitational interactions between a planet and the surrounding gas disk, the leading explanation for this inward migration, would naturally preserve the planet's original prograde orbit throughout the entire process. A misaligned, backward orbit under this view could only arise if the disk itself happened to be tilted relative to the star's spin from the very beginning, an unusual starting condition, rather than a common outcome. The discovery that changed this picture centers on a planet officially designated TIC 241249530b, a world roughly 5 times the mass of Jupiter, first detected by NASA's Transiting Exoplanet Survey satellite in January of 2020. The initial transit signal, the characteristic dimming of starlight as the planet crossed in front of its star, showed something unusual right away, a transit shape and depth, consistent with a Jupiter-sized planet, but on an orbit that did not match the comfortable, well-behaved patterns astronomers typically expect from giant planets. To confirm what they were looking at, the research team turned to 2 specialized instruments mounted on the WIYN 3.5-meter telescope at Kitt Peak National Observatory in Arizona. The first instrument, a speckle imager designed to freeze out the blurring effects of Earth's atmosphere, allowed the team to rule out the possibility that the signal was being caused by some background object accidentally contaminating the data, rather than a genuine planet orbiting the target star itself. The second instrument, a precision spectrograph called NEID, was the tool that revealed just how strange this planet's orbit truly was. By carefully measuring how the host star's light spectrum shifted in wavelength as the planet orbited, the radial velocity method described earlier, the team determined that the planet follows an extraordinarily stretched, elongated path around its star, with an eccentricity measured at 0.94. To put that number in perspective, an eccentricity of 0 describes a perfectly circular orbit, the kind most planets in our own solar system follow closely. An eccentricity of 0.94 describes an orbit so flattened, so extreme, that the planet's distance from its star varies enormously over the course of a single year, swinging from a very close, blisteringly hot approach at its nearest point to a much colder, far more distant point on the opposite side of that same elongated path. This is, by a wide margin, more eccentric than almost any other transiting exoplanet orbit ever measured with this level of precision. But the eccentricity alone, while remarkable, was not the detail that made this particular planet so scientifically significant. Using radial velocity measurements taken specifically while the planet was in the middle of transiting in front of its star, the research team was able to measure something called the Rossiter-McLaughlin effect, a subtle distortion in the star's measured spectrum that occurs only during a transit, and only because of a specific quirk of how rotating stars emit light. A rotating star has one side spinning toward an observer on Earth and one side spinning away, and this motion causes the light from each side to be very slightly shifted in wavelength, one side blue shifted, one side red shifted, in a pattern astronomers can map across the star's visible disk. As a planet crosses in front of that star during a transit, it blocks out a small moving patch of that pattern, and the precise way the star's overall measured spectrum distorts as the planet sweeps across that pattern reveals, with remarkable precision, the angle between the planet's direction of travel and the star's direction of spin. When the research team analyzed this distortion for TIC 241249530b, the result was unambiguous. The planet is moving in a direction opposite to its star's rotation, a genuine retrograde orbit, confirmed not through indirect inference, but through a direct, physical measurement of the relationship between the planet's path and the star's own spin. The probability that this result reflects pure measurement noise rather than a real retrograde configuration was calculated at less than 1%, giving the finding a confidence level that left little room for alternative explanation. This is where the story becomes genuinely forensic, in the truest sense of that word. A retrograde orbit is not simply an oddity to be noted and set aside. It is physical evidence, frozen into the present-day architecture of the system, of a violent event somewhere in that planet's past. Remember that ordinary disk accretion, the quiet, orderly process described at the start of this section, should produce prograde orbits as close to universally as anything in planetary science gets. For a planet to end up moving backward relative to its star's spin, something must have happened after formation to flip that planet's trajectory. Some dynamical event, energetic, enough to tear the planet's orbit away from the gentle, cooperative alignment it should have inherited from the disk that built it. The leading explanation under serious consideration for this particular planet is a process astronomers call high eccentricity tidal migration. Under this model, a giant planet does not form on the close, scorching orbit where we eventually find it. Instead, it forms much farther out from its star, in the colder outer regions of the original disk, on a perfectly ordinary, well-behaved prograde orbit, exactly where the standard model predicts a gas giant should condense. At some point afterward, while still young, that planet's orbit gets violently disturbed, either through a close gravitational encounter with another massive planet in the same system, a process called planet-planet scattering, or through a slower, more subtle gravitational tug from a distant companion star or planet locked in what is known as a Kozai lead-off cycle, a periodic gravitational interaction that can gradually pump up a planet's orbital eccentricity and tilt its inclination over many millions of years, eventually flipping the orbit's relationship to the star's spin entirely. Once an orbit has been stretched and tilted this dramatically, a second process takes over. Each time the planet swings through the closest point of its now highly elongated orbit, passing extremely near to its star, the star's powerful gravity raises tides on the planet itself, in much the same way the moon raises tides in Earth's oceans, except on a scale violent enough to physically flex and deform the planet's outer layers. This tidal flexing converts a small amount of the planet's orbital energy into heat with every single close pass, and over enough repeated passes, spanning millions of years, this gradual energy loss slowly shrinks and rounds out the orbit, pulling the planet's distant point closer and closer to its near point until the wildly eccentric, elongated path circularizes into the kind of close, compact orbit characteristic of a true hot Jupiter, a giant planet parked just a few days, or even just a few hours, away from its star. TIC 241249530b is, in this framework, caught directly in the middle of this transformation, a genuine snapshot of a hot Jupiter still being made. Its extreme eccentricity of 0.94, combined with its current orbital period of 167 days, places it firmly in the early, still elongated stage of this tidal migration process, long before tidal forces have had time to fully circularize its path into the tight, fast orbit that defines a finished hot Jupiter. This planet has not yet become a hot Jupiter. It is becoming one, observed live, in a configuration astronomers had predicted should theoretically exist as an intermediate stage, but had struggled for more than 2 decades to actually catch in the act. Despite the confirmation of over 5,600 exoplanets across that same span of searching, the connection between this planet and an earlier, similarly extreme world named HD 80606b adds further weight to the high eccentricity migration interpretation. HD 80606b, discovered with its own dramatically eccentric orbit, measured at 0.93, had previously stood as the strongest individual piece of observational evidence supporting the idea that hot Jupiters could form through this violent eccentricity-pumping pathway rather than through quiet, gradual disk migration alone. But HD 80606b existed for years as something close to a singular example, a single data point that could not, on its own, confirm that this formation pathway was common rather than a rare statistical fluke. TIC241249530b changes that calculation. Researchers had been actively searching for more than 2 decades for additional examples that would confirm high eccentricity tidal migration as a genuine, repeatable formation channel rather than an unusual one-off event, and the discovery of a second, independently confirmed world following the same extreme pattern. This time with the added confirmation of a measured retrograde orbit through the Rossiter-McLaughlin effect, provides exactly the kind of corroborating evidence the field had been waiting for. Arvind Gupta, the lead author of the research describing this discovery, framed the significance of the find in strikingly direct terms, noting that while astronomers cannot literally press rewind and watch planetary migration happen in real time, this particular exoplanet effectively serves as a snapshot of that very process, caught at a specific, intermediate moment that theory had predicted but observation had rarely managed to capture so clearly. The planet's retrograde motion is, in this sense, not simply an isolated strange detail layered on top of an already unusual orbit. It is the connective tissue linking the planet's extreme eccentricity to a specific, mechanistic explanation for how it got that way in the first place. Without the retrograde measurement, the planet's eccentric orbit alone might be explained through several different, competing scenarios. With the retrograde measurement included, the evidence narrows considerably toward the high eccentricity tidal migration pathway specifically, since that pathway, unlike most quieter, gentler migration mechanisms, naturally produces exactly this kind of dramatic misalignment between a planet's orbital direction and its star's spin as a routine byproduct of the violent gravitational interactions involved. It is worth being precise here about what remains uncertain, because not every detail of this planet's history has been pinned down with equal confidence. The research team's own analysis acknowledges that retrograde orbits of this kind, while strongly consistent with high eccentricity tidal migration driven by Kozai-Lidov cycling with a more distant companion, can also, in principle, be produced through the alternative mechanism of direct planet-planet gravitational scattering between 2 or more giant planets within the same system, without necessarily requiring any distant companion star or planet at all. Distinguishing definitively between these 2 specific violent pathways, a slow, cyclical tug from a distant companion versus a sudden, chaotic close encounter between planetary siblings, requires additional observations of the system that have not yet been completed, including a more thorough search for any additional bodies that might be present. What can be stated with confidence at the current stage of research is the broader category. This planet's orbit is the product of violent, dynamical disruption following its initial formation, not the product of quiet, orderly disk migration alone, and its retrograde direction stands as the direct, physical fingerprint of that disruption. Stepping back from this single system, the broader significance of a confirmed, well-measured, retrograde, hot Jupiter progenitor extends into one of the longest-running open questions in the entire field of exoplanet science, the question of how hot Jupiters, as a whole population, actually come to exist. This question has remained genuinely unresolved for more than 2 decades, ever since the very first hot Jupiter was discovered orbiting a star outside our own solar system, immediately overturning the assumption, built entirely on the example of our own solar system's architecture, that giant gas planets should always be found far from their stars, out in the cold, icy outer regions of any planetary disk, never parked in tight, scorching orbits just days or even hours from their star. Two broad families of explanation have competed to answer this question ever since. The first, called disk migration, proposes that hot Jupiters form in the expected location, far out in the cold outer disk, and then migrate inward gradually and smoothly through ongoing gravitational interactions with the surrounding gas of the disk itself, arriving at their final close orbit while still embedded within that disk before it has fully dispersed. This pathway, because it keeps the planet continuously embedded within the smoothly rotating disk throughout its entire journey inward, naturally predicts that the resulting hot Jupiter should retain a prograde orbit, well aligned with its star's spin, since nothing in this gentle, gradual process provides any strong mechanism to tilt or flip that alignment along the way. The second explanation, the high eccentricity tidal migration pathway directly relevant to TIC 241249530b, predicts something different, a population of hot Jupiters that should frequently show misaligned, sometimes fully retrograde orbits, precisely because this pathway depends on violent, eccentricity-pumping gravitational disruption rather than smooth, continuous disk interaction. For years, observational surveys measuring the spin-orbit alignment of confirmed hot Jupiters found a genuinely mixed population, some well-aligned and prograde, consistent with quiet disk migration, others significantly misaligned, some even fully retrograde, consistent with the more violent pathway. This mixed results suggested that both formation channels are likely real, operating simultaneously across the broader galactic population of hot Jupiters with different individual systems, following different paths, depending on their own specific history and the presence or absence of additional companion bodies capable of triggering the more violent route. What made TIC 241249530b such a valuable addition to this picture is that it does not simply add one more data point to the existing tally of aligned versus misaligned hot Jupiters. It captures a progenitor, a planet caught before it has finished the transformation, still carrying its full, dramatically elongated eccentricity, rather than the already circularized orbit of a finished hot Jupiter. Nearly every previously confirmed retrograde hot Jupiter in the existing population represents an endpoint, a planet that has already completed its tidal migration and settled into a final, tight, circular orbit, its earlier eccentric history erased by the very same tidal forces that brought it inward. Finding a planet still in the dramatically eccentric, not yet circularized intermediate stage, and confirming that even at this earlier stage it already carries a measurable retrograde misalignment, provides direct observational support for a specific causal sequence. The misalignment is established early, during the violent disruption event itself, well before tidal circularization finishes the job of shrinking the orbit down into its final, compact form. This single confirmed world, in other words, does not just break the simple, prograde-only version of planet formation theory. It actively helps resolve, with real observational evidence, rather than theoretical inference alone, a genuine decades-long uncertainty about how an entire major category of planet, the hot Jupiters, that astronomers have now confirmed in the hundreds across the galaxy, actually came to exist in the configurations we find them in today. The rulebook did not simply fail to predict this planet. The rulebook's own internal uncertainty about giant planet migration is being actively narrowed and clarified specifically because this planet exists and was caught through painstaking, multi-instrument observation in precisely the intermediate state needed to distinguish between competing explanations. 3 categories of rule-breaking world have now been examined in full, each one challenging a different layer of the same underlying theoretical framework. A planet's measured density should match a calculable prediction based on its mass, its radius, and its presumed composition, and TOI 561b and GJ367b each violate that prediction in opposite directions. 1. Impossibly light. For a world baking this close to its star. 1. Impossibly dense. Sitting on the narrow theoretical line reserved for a world stripped down to almost pure iron. A planet should be bound to a star, inheriting its very identity as a planet from that gravitational relationship, and the free-floating worlds confirmed through both microlensing near the galactic center and direct imaging within the stellar nursery of NGC 13337 sever that relationship entirely, existing as fully formed planetary bodies, with no star, no orbit, no year, drifting through the dark space between systems. And a planet should inherit the same direction of travel as the very star and disk that built it, and TIC 241249530b moves in direct, measured, confirmed defiance of that inheritance, carrying within its backward orbit the physical fingerprint of a violent gravitational event written into its trajectory and preserved there for astronomers to read, millions of years after the event itself took place. 3 separate categories. 3 separate, specific physical predictions, each one calculated from the same foundational theory of how planets form. 3 real, confirmed, precisely measured worlds, each one breaking a different prediction in a different way, for different, individually well understood physical reasons. The question that remains, now that all 3 categories have been laid out individually, is what happens when you stop looking at them one at a time, and instead step back far enough to see what they reveal together, as a single connected pattern rather than 3 isolated curiosities. Lay these 3 categories of worlds side by side, and a pattern begins to emerge that none of them reveals fully on its own. TOI 561b and GJ367b broke a prediction about composition. The free-floating planets of NGC 1333 and the microlensed world near the galactic center broke a prediction about gravitational belonging. TIC 241249530b broke a prediction about direction of travel. 3 entirely different categories of violated expectation, and yet every single one of them traces back to the exact same underlying cause, examined from 3 different angles. Planet formation, it turns out, is not a single clean recipe executed identically every time a star and its surrounding disk come together. It is a violent, competitive, frequently chaotic process, one that happens to produce calm, orderly, well-behaved outcomes, often enough that astronomers were able to build a coherent theory around those common results, but one that just as routinely produces the rare, extreme exceptions explored across this entire documentary. This reframing matters enormously for how the original rulebook should actually be understood. None of the 3 anomaly categories examined here required astronomers to throw out planet formation theory and start over from nothing. The basic physics underlying disk accretion, photoevaporation, gravitational ejection, and tidal migration all remain intact, fully consistent with everything else known about how stars and planets form. What changed, in each case, was not the physics itself, but the assumption that the physics would always produce a narrow, predictable range of outcomes. TOI 561b did not break the physics of photoevaporation. It revealed that an actively replenished volatile envelope sourced from a churning magma ocean below can outpace that photoevaporation process under the right circumstances, something the simplest version of the model had not accounted for. The free-floating planets did not break the physics of gravitational dynamics within a young, crowded planetary system. They revealed just how routinely those same dynamics, when sufficiently chaotic, eject entire fully formed planets out of their systems entirely, alongside a second, independent pathway through direct cloud collapse that does not require a system to eject a planet from at all. TIC 241249530 B did not break the physics of tidal migration. It provided the missing observational link, confirming that this violent pathway, long predicted in theory, genuinely operates in practice, captured at precisely the intermediate stage needed to prove it. This is, in many ways, exactly how a healthy scientific field is supposed to function, though it rarely gets framed that way in popular discussion of new discoveries. A theory built from limited early data makes its best, most confident predictions. New instruments, more sensitive, more precise, capable of measuring details the original theory's founders could never have directly observed, get pointed at the universe. Some of what those instruments find confirms the original predictions cleanly. Some of it does not. And when it does not, the response within the scientific community is not to abandon the underlying framework, but to ask a more specific, more useful question: what additional physical process, previously unaccounted for, is needed to explain this particular exception, without breaking everything the framework still gets right elsewhere? Photoevaporation models needed an additional mechanism for ongoing volatile replenishment from active magma oceans. Ejection-based models of free-floating planets needed a second, independent formation channel through direct cloud collapse, layered alongside the original ejection pathway. Disk migration models of hot Jupiter formation needed a second, violent, eccentricity-driven pathway running in parallel alongside the original gentle, gradual mechanism. In every single case, the theory did not collapse. It grew more detailed, more layered, more capable of explaining the full range of what astronomers actually observe, rather than only the simplest, most common cases. This pattern carries a direct and meaningful consequence for one of the deepest, most persistent questions in all of astronomy: the search for life beyond our own solar system, and more specifically, the question of how common or how rare a planetary system like our own actually is across the wider galaxy. For decades, much of the public conversation around exoplanets has implicitly treated our own solar system's architecture: small rocky worlds close to the sun, gas giants farther out, stable, nearly circular, orbits maintained over billions of years without major disruption, as something close to a default outcome, with departures from that pattern treated as unusual edge cases worth special attention specifically because they are unusual. The growing population of density anomalies, free-floating worlds, and retrograde giants examined throughout this documentary suggests a meaningfully different picture. Our own solar system's calm, orderly, undisturbed architecture may itself be one outcome among a genuinely wide range of possible outcomes that planet formation is capable of producing, rather than the expected, default result from which everything else represents a deviation. If violent ejection events are common enough to leave the galaxy, in the words of the researchers who confirmed the January 2026 microlensing detection, teeming with free-floating planets, then it follows directly that violent, system-disrupting events of various kinds, the same broad category of chaotic gravitational interaction responsible for ejecting planets entirely or flipping their orbits into retrograde configurations, must be a routine part of planetary system evolution across the galaxy as a whole, not a rare aberration confined to a small number of unlucky systems. Our own solar system, by this framing, either avoided this kind of disruptive history through some combination of fortunate initial spacing and timing between its forming planets, or it experienced its own version of this violence in its deep past, and we simply do not have direct evidence of any planets we may have lost along the way, ejected long before recorded astronomy began. Both possibilities remain genuinely open, and current research has not settled which one describes our own system's actual history. This question connects directly to ongoing, active research into the long-term dynamical stability of our own solar system's architecture, an area of study that has, independently of the exoplanet discoveries described throughout this documentary, already revealed that our system's current configuration, while stable across the time scales relevant to human civilization, is not guaranteed to remain stable indefinitely across the full span of cosmic time, still remaining before the Sun itself eventually changes in ways that will reshape the inner solar system entirely. The same fundamental gravitational dynamics responsible for ejecting planets in other systems entirely, or twisting their orbits into the kind of dramatic, retrograde configuration measured directly in TIC 241249530b, remain mathematically present within our own solar system's long-term orbital calculations as well, operating on time scales so vast, hundreds of millions to billions of years, that they have not yet produced any comparable disruption within our own neighborhood, but operating according to the very same underlying physics nonetheless. The instrument poised to bring the clearest answers yet to these open questions is the Nancy Grace Roman Space Telescope, repeatedly referenced throughout this documentary's earlier sections as the mission specifically designed to expand the microlensing search for free-floating planets far beyond what current ground-based surveys are capable of detecting. Roman's relevance extends well beyond that single category of anomaly, however. Its wide field of view and exceptional sensitivity are expected to dramatically expand the total confirmed population of exoplanets across every category examined in this documentary simultaneously: density outliers, free-floating worlds, and misaligned giants alike, providing the kind of large, statistically robust sample size needed to finally answer questions that the current, comparatively small population of confirmed extreme worlds can only gesture toward. How common, precisely, are ultra-short period planets that retain unexpected volatile envelopes? What fraction of all giant planets across the wider galactic population carry measurably misaligned or fully retrograde orbits? And does that fraction match what the high eccentricity tidal migration pathway alone would predict? Or does it suggest some additional mechanism still waiting to be identified? How many free-floating planets, in total, actually drift through our own galaxy? And what proportion of that total population traces back to violent ejection rather than independent formation through direct cloud collapse? None of these questions has a fully settled answer at the moment this documentary was written, and that absence of a final answer is not a weakness in the story being told here. It is, in fact, the most honest possible place to end it. The three worlds examined across this documentary, TOI 561b, with its impossibly retained atmosphere, the free-floating planets drifting without any star to call their own, and TIC 241249530b, caught mid-transformation on its backward orbit, were not selected because they represent the final word on what planets are capable of. They were selected because each one, individually, forced a specific, well-defined revision to a specific, well-defined piece of planet formation theory, and because, examined together, they reveal that the universe's capacity to produce planetary outcomes is wider, stranger, and more varied than the cleanest version of the textbook ever assumed. There is something worth sitting with in how each of these discoveries actually happened, because the process itself says as much about the nature of scientific understanding as the discoveries do. Nobody set out looking for a planet that shouldn't exist. Astronomers pointed survey telescopes at the sky, looking for ordinary transits and ordinary radial velocity signals, the same routine measurements that have confirmed thousands of perfectly unremarkable planets, matching every prediction comfortably. The anomalies emerged only when those routine measurements were compared carefully against what the existing theory predicted. And the gap between prediction and observation turned out to be too large, too consistent, too well measured to dismiss as noise or error. This is a meaningfully different story than the one suggested by a title promising an unexplainable planet. These worlds are not unexplainable. They were, in every case examined here, eventually explained, sometimes within months of the anomaly being first noticed, sometimes after years of additional observation using progressively more capable instruments, but explained nonetheless, through the same patient, evidence-driven process that built the original rulebook. Those planets initially appeared to violate. What makes this worth dwelling on, rather than treating as a minor technical footnote, is what it reveals about the actual relationship between a scientific theory and the universe that theory is attempting to describe. A theory is never the universe itself. It is always a model, a simplified, necessarily incomplete description built from whatever evidence happened to be available. At the moment the theory was constructed, refined continuously as new evidence arrives, capable of being wrong in specific, identifiable ways without being wrong in its broader, foundational structure. Planet formation theory correctly identified the basic physics of disk accretion, the basic division between rocky and gas giant worlds, the basic mechanisms of planetary migration, decades before any of the three anomaly categories explored in this documentary were ever confirmed through direct observation. That foundational structure has not been overturned by TOI 561b, by the free-floating worlds of NGC 1333, or by the retrograde orbit of TIC 241249530b. It has been extended, refined, and made considerably more precise by the existence of these three worlds, in exactly the way a foundational structure is supposed to respond when confronted with genuine, well-measured evidence that does not fit its simplest original predictions. This is, in the end, what separates the phrase "shouldn't exist" from the phrase "doesn't exist," and the distinction is not a small one. Every single world examined across this documentary does exist, confirmed through multiple independent lines of evidence, measured with enough precision to calculate exact density values, exact orbital eccentricities, exact spin-orbit misalignment angles. What shouldn't exist, more precisely, was never the planet itself. It was a specific, narrow version of a theoretical prediction built before anyone had the instruments capable of testing that prediction against the full diversity of what the galaxy actually contains. The planet was never the mistake. The assumption that the simplest version of the model would hold universally, without exception, across every planetary system in the galaxy was the mistake, and it is a mistake. The scientific process is now in the process of correcting one precisely measured, individually confirmed, genuinely strange world at a time. Consider, for a moment, what it actually means that a single planet, 10 times smaller than Jupiter, orbiting a star most people will never hear the name of, sitting 540 light-years from the nearest human observer, was capable of helping resolve a question that had remained genuinely open within professional astronomy for more than 2 decades. TIC 241249530b did not announce itself with extraordinary brightness or unmistakable visual spectacle. It revealed its significance only through a careful, technical, multi-instrument measurement of a subtle distortion in starlight, the kind of result that exists entirely within data tables and statistical confidence intervals, rather than anything resembling a dramatic image. And yet, that quiet, technical measurement did more to clarify how an entire major category of planet comes to exist than years of broader theoretical speculation had managed to accomplish on its own. The same is true of the careful density calculation that revealed TOI 561b's impossible atmosphere, and the painstaking, years-long microlensing survey work that finally pinned down both the mass and the distance of a single, free-floating world drifting alone near the galactic center. None of these discoveries arrived through a single, dramatic moment of revelation. Each one arrived through patient, incremental, technically demanding work, the unglamorous foundation underneath every genuinely significant scientific advance. The honest place this story arrives, after walking through all 3 categories of impossible world, is not a place of mystery left unresolved, and it is not a place of triumphant certainty either. It is something quieter and more durable than either of those framings. These planets shouldn't exist only within the boundaries of a specific, narrower prediction that astronomers themselves have since outgrown. The universe was never confused about how to build them. It built them the same way it builds every planet, through the same underlying physics operating across the same basic process of disk accretion, gravitational interaction, and long-term dynamical evolution. What was incomplete was never the universe's method. It was the small, specific corner of human understanding that had not yet caught up to the full range of what that method was always capable of producing. Every backward orbit, every impossibly retained atmosphere, every world drifting without a star, stands as a direct, physical record of how much more inventive the ordinary, well-understood laws of physics turn out to be once enough of the universe has actually been measured closely enough to see them at work.